everyone, welcome to Learning at 11th Hour. So today we are going to continue with the number system. In the last video, I talked about converting a decimal number into a binary and a binary number into a decimal number. So today we are going to look at more conversions. So we're going to see how we can convert an octal number into binary and vice versa. So when we talk about octal numbers, octal as in 8. So the number of symbols that is going to be available in this number system is going to be from 0 to 7. So there are 8 symbols. So if I have just one digit, then the range of numbers would be from 0 to 7. If I have two digits, then how many numbers or what is the range of numbers that I can represent? So there is a generalized formula to find that out. For example, let's look at binary. We'll start with a simple one. So we have two symbols, 0 and 1. If we have just one bit, then you can have either a 0 or you can have a 1 over here. So that means if I have a 1 bit number, then 2 to the power 1. 2 is because there are two symbols, 0 and 1. So this represents the number of symbols and the power represents the number of bits. So here we have 2 to the power 1, which is 2. So you can have two numbers, 0 and 1. But if I say I have two bits, I want to represent a number with two bits. So what are the different numbers that I can represent using two bits, or what is the range of numbers that I can represent using two bits? So I have two bits over here. So the number of bits, that is the power value, is going to be 2. And the number of symbols is still 2 because we're talking about the binary number system. So we'll have 2 to the power of 2. So 2 power 2 is 4. So the number of uh, combinations that are possible using zeros and ones for a 2-bit number is 4. So what are the different combinations? So you can have 0, 0, 0, 1, 1, 0 and 1, 1. So these are the four numbers. Similarly, if I look at an octal number, so if there's just one digit, so in that, how many numbers can I have? So I can have 8 to the power 1, where 8 is the base of the number system and this power represents the number of bits. So here 8 power 1 is 8. So I can have 8 numbers from 0 to 7. On the other hand, if I have two digits in this octal number, so then I'll have the base is 8 and the power here is 2. So 8 square, which is I can have 64 numbers. So the numbers would range from 0 to 63. So this is how we can generalize as to how many numbers can be represented, having given the base of the number system and the number of bits that are available in the number system. Let's try this for hexadecimal. So for hexadecimal, we know that the base of this number system is 16. And if I have, say, two digits, two positions or two bits that I can use to represent. So two positions can be used. So 16 to the power 2, which is 256. So I can go from 0 to 255. These are the range of numbers that I can represent using two digits in the hexadecimal system. So this 256 and the 0 to 255 range that I'm talking about, all of these are actually decimal numbers. Since we are very familiar with the decimal system, so it will be able to understand the interpretation of the range of numbers, which is why I'm saying 16 square is 256 and I'm talking about the decimal system in this case. So for a hexadecimal system, we can represent 256 numbers using two digits. So let's move on to the actual conversion from octal to binary and binary to octal. So before we go into the conversion, there's one more thing that we need to understand. So this is, say, the octal numbers 0, 1, 2, 3, 4, 5, 6 and 7. Now what is the binary representation of these numbers? So 0 we are going to represent the octal number as a 3-bit binary number. That's how it works, because 2 to the power 3 is going to be 8. We need to represent 8 numbers starting from 0 to 7. So we need, how many bits of binary numbers do we need to represent 8 numbers? So how can we find that out? So we know that the base of the number system is 2. We need to find out the number of bits, and we know that there are 8 symbols that need to be represented. So then taking log on both sides, so we get x log base 10 2 is, this is 2 power 3, isn't it? So we can rewrite this as 3 log base 10 2. So therefore, equating the two, the right hand side and the left hand side, we get x is equal to 3 over here. So which means what? This was the base, and this was the number of bits that are required so that we can represent 8 numbers. So the number of bits here is 3. So we can represent an octal number as a 3-bit binary number. So 0 would be all zeros. What is 1? 0 0 1. What is 2? 0 1 0. Now how am I writing all this? So instead of memorizing the sequence, it is better to do it logically. So there is a simple way of doing it. So there's something called the 8421 code. In this case, we are not going to use this 8 because ours is only 3 bits. So I'll call it as a 421 representation. So let me remove this 8 for the sake of simplicity. Now I want to represent 0. So I'll put 0 in all of these positions. If I want to represent a 1, I'll put a 1 under this 1. If I want to represent 2, I'm going to put a 1 under this 2, and the rest of the positions are going to be 0. Now I want to represent 3. So 2 plus 1 is 3. So both of these bits are going to be involved. So I'll place 1s over here and put a 0 here. I want to represent 4. So there's already a 4 over here. So I'll put a 1 here and put the other two positions as 0. Next, I want to represent 5. 5 is 4 plus 1. So I'll put 1s in those positions and the rest of the positions is going to be 0. For 6, I can say 4 plus 2. So 4 and 2 will have 1s in this position and the rest of the positions will be 0. For 7, it is 4 plus 2 plus 1. So all the 3 positions are going to be 1s. So this basically becomes the binary representation of octal numbers. So I hope right now we are clear with the fact that we need 3 bits to represent an octal number using binary representation. I hope the reason for that is also clear as explained over here. Okay, now I have filled up the binary column also. So from this, it's kind of a lookup table for us right now, right? If I want to convert 2 into binary, octal 2 into binary, how would I do it? So I could just look up this thing over here. So 2 octal would be actually 010. But if I have more than one digit in a number, then how do I perform the conversion? So for that, I need to split up my binary representation into groups of 3, or represent each digit in my octal number into a 3-bit binary number. So let's take up some example to understand what I just said a little more clearly. So let's take the example. Say I want to convert from binary to octal first. So I have a binary number, say something random like this, and I want to convert it into an octal number. So we know that every number in the octal number system can be represented using a 3-bit binary number. So what we are going to do is we are going to split up this binary number into groups of 3 bits. And I'm going to start from the rightmost bit, that is the least significant bit, and move upwards towards the most significant bit. So I'll put a partition here, 1 2 3, partition over here, and since I just have 2 bits here, I can pad it with a 0, and then this forms my third group. So now I can say that the first step is to split the binary number into groups of 3 bits. So after this, what do I do? After this, we need to represent each of these 3 bits with the octal number. So if you wish, you could actually look up and find out what is the corresponding octal number for these binary numbers, right? So if we see 110 is actually octal 6, 101 is 5, and 010 is 2. So therefore, we can say that this particular binary number 010 101 110, actually the number didn't have a 0 in the beginning because we padded it. So this binary representation can be written as 256 in the octal number system. So the second step here, we can therefore say that write the octal equivalent of each group. Let's take up an example where we need to convert an octal number into a binary number. So say I have a number, say 465. This is octal. Is this a valid octal number? So if the symbols used in this number are in the range 0 to 7, then it is absolutely a valid octal number. If there is some number like 468, now 8 is greater than 7, so this is not an octal number, right? So now I want to convert this octal number 465 into a binary number. So what I'm going to do is I'm going to represent each of these digits in this octal number using a 3-bit binary number. So 5 is going to be 101, 6 is 110, and 4 is 100. Therefore, the binary representation becomes 100, 110, 101. So it is as simple as that. That's all with today's video. I hope the concept of converting an octal to binary and vice versa is clear to you all, and why we represent the octal with the 3-bit binary number is also clear to all of you. Please do subscribe to this channel to watch more such videos on digital electronics. Thanks for watching.